x over 4. I approach my formula booklet. I know that the derivative in general is 1 over root 1 minus whatever x is squared, and x is this in this case. And then afterwards, I'd have to multiply by the derivative of any function inside. What's the derivative of this? X over 4? 1 over 4. So I didn't. So you don't need to flip. You just put you can put the 4 in front here. You can square this out if you really want to, but I'm okay with this so far. That's fine. You can put 1/4 of this or 4. Okay. This second example then, r cos sine x. So we go to our formula booklet. R cos is minus 1 over root. It's 1 minus x squared, yes. 1 minus whatever x is squared. Now this is sine x, so minus sine squared x. I got to multiply that then by the derivative of this, which is cos x. Very good. Now, this one I'm going to tidy up because it's quite nice. What is 1 minus sine squared?
Cos squared.
Yeah, so cos squared x plus sine squared x is equal to 1. So cos squared x is equal to 1 minus sine squared x. So that equals that. So the square root of cos squared x is cosine, isn't it? So I can write it. So this is 1 minus root cos squared x times cosine x, yeah? So I've seen that is equal to that. The square root of cos squared is just cosine squared. That's 1 over cosine x times cosine x. So they cancel, and just minus 1. So that's quite nice.
Nice.
Nice indeed.
Nice.
Okay, so we're moving on. All those rules we'll have to apply at some stage. We haven't really looked at any problems in context yet. We're also going to move on to, that's the next chapter really, where we look at these in more context in real life. What?
In real life.
Yeah, in real life.
In real life,
I or L.
cos tan squared x sine on theta.
Yeah, so, right. So, if we think about something's distance from a particular point, or displacement from a particular point, and we plot that on a graph, and time is this axis, and the displacement or distance from a point is on this axis, and it looks, I don't know, something like this. Whatever, it's further away, and then it comes a little bit closer, and then it's starting to go further away, and stuff like that. Does that make sense? Okay, so this is like distance or displacement. S in physics, isn't it? Okay. If I want the gradient any particular place along that, what would the gradient show?
The velocity.
Yeah, the rate of change of displacement or distance, the change in distance over time. So change in distance over time is speed or velocity, yeah? Velocity, I suppose, is technically more correct. What happens if I got a new graph then of all the gradients. So uphill, 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 downhill, downhill a little bit, uphill, 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 uphill. So that's positive, negative answers. So it might look something like that, maybe. Something like that. What would the gradient of this one be? Yes. Very good. So the gradient of the gradient, or the derivative of the derivative, would show me the change of velocity over time, because this is now the velocity function. So the changes in this one will be the acceleration function, how much the velocity is changing with respect to time. So that would be then a second derivative. So if we had my original function, that's fx, this is f dash x, and if I derive this one again, I would get f dash dash x, the second derivative, which will tell me the acceleration of the function. So positive, 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 negative, 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 negative. Or sorry, I did that wrong. I was looking at the gradients. Negative, 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 positive. I'm just looking at the gradients. Positive, all uphill. So it's increasing, it's accelerating after this point, it's decelerating at a certain point. The acceleration is 0, stuff like that. Okay? So that's sometimes why we might need to get the second derivative. At the moment, we're just going to get the second derivative without context. Later on, we'll do this stuff, which is a whole chapter in the book, which begins with the letter K. Does anyone know what it finishes?
Kinematics.
Unbelievable.
Why do you physician here?
So we will do kinematics pretty soon. So bear that in mind, why we need the second derivatives. Before we do a couple of second derivative problems, let's do them now. If a screen wasn't frozen, that'd be a lot better. Which way? This way. They were the answers. -1 was correct. Okay, let's look at second derivative problems. Right. These are not looking so nice, maybe. I'll do these. You'll help me. Well, you'll be here. X cosine x plus 1 over x. Okay, get the second derivative of this. Try and beat me to it if you think you know what to do. All right, so second derivative means I have to find the first derivative and then derive that again. So my first derivative, or gradient function, will be, thoughts? Alex, what do I do here when we wake up? Well, product rule, thanks Derek. Product rule. Right. First by derivative second plus second by derivative first, or some version of that. X sine x, but that's a minus, yeah? Plus cos x times 1. What's the derivative of 1 over x again?
-1.
1 x.
-1. Negative x to the power of -2.
That's why I like sometimes just to rewrite it before I start, because I think it's going to be easier if it's written like
X to the power of -2.
-1x.
Negative x to the power of 2. -2.
Negative, all right. Very good. That is the first derivative. Let's get the second derivative, the gradients of the gradients, the rate of change of the rate of change. All right, so we got to use what here? This one. Product rule again. Okay. First by derivative second. Plus second by derivative first. Sine x times -1. So that will make that a negative. What's this one?
Plus 2x to the power of -3.
There we go.
That is something.
So -2 times -1 is +2. Take 1 away from -2. All right, let's do the second example I have here, which is find the third derivative of cosine 2x. And then sub in something. So cosine 2x, first derivative of cosine 2x, flawlessly done, will be Mire. What is it?
Don't know. Don't.
Come on.
It's -2x.
Minus sine 2x
Plus 1.
Minus sine 2x 2.
times 2, yes. Which is -2 sine 2x. Remember, derive the inside thing. All right, now second derivative is
-2 cos.
-2 cos 2x
Times 2.
times 2 again. So that becomes -4 cos 2x. Third derivative,
Alright.
because I asked for it. -4. You,
What is not positive? Positive 4.
very good.
Times 2.
What?
8 sine 2x.
Now they want us to substitute into the third derivative. So you can write f3 or f with 3 dashes. They want to sub something in. That pi over 8
Pi by 4.
equals what? Well, that's 8 sine pi over 4. What's pi over 4? Sine pi over 4? Quick, Trig.
45.
No,
Oh, like the whole thing?
Sine, what's sine 45?
Oh,
1 over... I prefer root 2 over 2 because I've looked at the answer. And that, we'll go into that 4 times. We get 4 root 2. Indeed.
1/√2 just sounds better.
No.
No, it doesn't. So
I don't like you saying 1 by root 2.